Welcome to Lesson 7D, General Ventilation. We're starting something new now. We're going to look at general ventilation. Pretty much all of Chapter 5 has to deal with general ventilation. I'll first discuss what it means, and then we'll look at two different types of ventilation in rooms, displacement and dilution. We've spent a lot of time just learning some of the fundamentals and then how to predict source strength of contaminants by various methods, emission factors, and then we spend some time on evaporation. Now we're going to look at ventilation in rooms or a building. First, I want to talk about general ventilation versus local. General ventilation is ventilation in a whole room or a building. This is kind of the meat of the course here, these two topics, general and local ventilation. In a typical room, you might have a source of some contaminant, and then you have some air that's coming in. We call this supply air. And then you have some air going out some other location. We typically call this return. It may go outside or it may return through some ductwork and filters and stuff back into the building or into the room. And then local ventilation is where we're looking at basically hoods. And this is Chapter 6. So instead of worrying about a whole room, we have a ventilation hood, something like this. And this goes off to some pipe. There could be a blower and going to some elbows and stuff. So we'll look at the fluid dynamics of what happens to the air plus contaminant that goes through that hood. We still are talking about some kind of a source here. The idea is to collect the vapors or the particles from that source into the hood, and the general term for that is local ventilation. We're going to concentrate now on general ventilation, and within the ventilation topic, there are two types: dilution and displacement. So I'm going to talk about dilution. This is the one that we'll spend most of our time on. We are going to assume well mixed. Here's our room. We have some fresh air coming in to this room. CJA, the ambient supply air coming in, and then some other place you have air going out, return air. We'll assume there's some kind of a mixing fan in here, and therefore it's well mixed. If I measure CJ any place in this room, including right at the exit. Now, it won't be true right at the inlet, so there'll be some region around the supply zone where obviously you have fresh air coming in. We kind of ignore that and assume that there's all these big eddies mixing things up, and once you're a little bit distance away from that supply inlet, everything is well mixed. I'll typically draw a fan to show that. Mathematically, CJ is CJ of time only. It's not a function of space. Of course, if it's steady, if you reach steady state conditions, then CJ is a constant everywhere. In our room, it's not even a function of time once you've reached steady state. Now let's contrast that with displacement ventilation. And that's a very different animal. The goal is to not be well mixed. Most American homes and businesses, offices want the room to be well mixed. So you may have a ceiling fan, or even if you don't, they design these diffusers on this supply air so that it pushes the air in various directions, and then you're drawing air in other directions, and it's assuming that you're setting up these big eddies, even if you don't have a fan, so that the air is well mixed. Displacement ventilation is the opposite. We don't want well mixed. So generally what we do there is we have our room. In both these cases, we have some kind of a source, SJ, of contaminant. The idea is that you supply the air in a nice, gentle way on the lower part of the room, and then you have the return in generally some bigger opening to go out. So this is the return. This is the supply. Dilution ventilation works for both heat and air conditioning. Displacement is generally for air conditioning only. We don't use this for heat. The reason is because you have cool, clean air coming in, and the idea is that this air stratifies so that you have warm air up here, warm air rises, and you have cool air down here, and it sort of stratifies, and then we assume there's a source that is buoyant. So the air tends to go up here, and you have some slow eddies moving back down to take its place. In the ideal situation, you wouldn't even have that. You would just have a clump of cool air that rises slowly. You're displacing. This is like a piston, and the source just kind of comes up and goes out. this plume of contaminated air. The rest of the air kind of has a piston effect like we talked about with filling tanks that displaces the air and just pushes it up. That's more popular in Europe. I wanted to just mention that CJ is a function of X, Y, Z, and T. Now it's not well mixed. So if I measure the concentration here or here or here, it's going to be different at various places. It'll be pretty clean air everywhere, and here this would be much more contaminated air, and this would be very clean air. What I want to do is go through a little slideshow that I have on my websites called Dilution versus Displacement Ventilation. This is parts of talks that I've given through the years on this topic. This is dilution ventilation. Mixing is enhanced. You have generally some kind of a fan going. We modeled a computer, a table, and a person sitting there. You can either have the supply here and the return here. A lot of U.S. offices, supply and the return are both in the ceiling. That's the way it is in my office that I'm sitting in right now, actually. It's used for both heating and cooling. Displacement ventilation, we have cool air coming in, and then you have some kind of buoyant plumes from heat from the person, from the computer, that goes up to the return. There's natural convection up. Mixing is suppressed. We don't want it to be well mixed. You want to keep any contaminants from this person within his zone here and above him. It's more common in Europe, best used with cooling. Displacement ventilation is also called buoyancy-assisted forced ventilation. You introduce cool, fresh air near the floor, and warm, contaminated air is removed from the ceiling. And as I mentioned, the displacement effect acts like a piston pushing the air upward. That's why we call it displacement ventilation. And we're assuming horizontal stratification, warm air near the top, cool air near the bottom, and natural convection, not forced convection, is relied upon. And there's a reference if you want to study that a little more. Again, it's for cooling and useful for removing contaminants. You can have better air quality because you don't mix the contaminants. So dilution ventilation, any contaminants in the room get mixed up all over the room, so every place has the same contaminated air concentration. Displacement ventilation allows the contaminants to stay above where they're produced, assuming it's a buoyant plume, and everywhere else has much cleaner air. Here's an example. We actually had a little bit of funding to study this for applications in offices back when people were still allowed to smoke. But it applies to anything. If this guy has COVID, this guy doesn't, and you put in a fan and you mix the air up, whatever he's breathing is going to go all over the room. Whereas in displacement ventilation, the thermal plumes from the person and the hot computer will rise, and in this case I'm showing smoke, but that can just as easily be some kind of contaminant from his breath. So it is possible in the air conditioning situation to have better air, especially for this person, and for him as well, because all the cool air is coming up from the bottom and his contaminants are being blown away. If you had dilution ventilation, everything would be the same everywhere, so all this smoke or contaminant would be mixed up in the air everywhere in the room. We did some Schlieren experiments where we had cool air from an air conditioner coming in, just like we had sketched, person sitting at a computer. You can see the thermal plume coming off, not so much the person, but the computer. That plume rises. What I did was some CFD, some computational fluid dynamics of that same thing, just with a Tin Man kind of figure and a computer. So we tried to imitate this picture, and you can see that we're capturing this thermal plume pretty well. And so that was a successful application. About 10 years later, in 2010, I had another project with these coworkers. We looked at poultry houses, chicken houses, using CFD. Here's a hen that I borrowed from the Penn State, the poultry barns, took it to our lab and took this picture of the thermal plumes. Chickens are warm-blooded creatures, so they're warm to the touch and they have a thermal plume just like a person does. I tried to do this without the cage, but I couldn't get the chicken to stand still, so I kept her in a cage. But anyway, that's the principle. In the United States, you go to a typical farm that raises chickens in the chicken house. The way the ventilation system works is the air comes into the attic through this intake. It goes through these diffusers through the ceiling, and then it comes out these exhausts. And it's a dilution type of ventilation system because it tries to distribute that air everywhere and mix it all up in these are caged chickens. Here's what it looks like from the outside. These are these exhaust fans coming out from a chicken barn that we visited. There were 6 of those fans in that case. What we suggested and did some research on, this was all CFD. We haven't tried it experimentally yet in an actual barn, but just reverse the flow. So what if we bring the air in from the side? Cool air, we're talking about in the summertime, these chickens are all hot. They all have thermal plumes. It's hot in there. You have to have ventilation. Bring the air in cleanly and let it displace up and then come out into the attic and exhaust out the top. So it's the exact opposite direction. We use the same geometry, but the opposite direction of the dilution case. So what were the results? We did computational fluid dynamics. We modeled 2 chicken houses in tandem, so the wind is coming from left to right. This is a species contaminant. We picked a substance. Back then we were interested in avian flu. Once a chicken gets it in one of these barns, it basically spreads through the whole thing and can even spread to other barns. This is a case where the contaminant was generated in this first barn. The wind is going from left to right. There's a big vortex and stuff, and it gets drawn into the attic and into this barn. This one has a smaller concentration, but there's still a lot of the contaminant from this first barn into this second barn. And then we're comparing the downward flow, the normal dilution case, with the displacement case here, where we're exhausting the air out the top. The colors themselves, the oranges are high concentration and white is extreme high concentration. We're doing a better job. I'll show you a blow up of that. This is the first barn for case 1 of the normal ventilation from top to bottom. Exhaust out the sides. White here means that it's off the chart. We had one chicken that was contaminated right here, and she spread this contaminant all over the rest of the barn. In the case of the displacement type ventilation, here's where the chicken is contaminated here, and there's a thermal plume because these chickens are warm-blooded, and so it goes right out the top. There is some spread. When there's that big vortex, some of that contaminated air comes back in and affects these chickens, but some of these chickens in the middle, they're still breathing some fairly pure air, so they don't get contaminated. And then we also looked at temperature contours. So that was an interesting project. You can see where this can apply to buildings as well, not just animals like chickens, but offices and stuff. And for coronavirus.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.